In this exercise, we study the velocity of air going through the trachea, and the equation for the velocity is given. We have v equals k times capital R minus small r times r squared. That's the velocity going through the trachea. K is a constant. Capital R is also a constant. It's the radius of the trachea at rest. And small r is the variable. It's how much the radius of the trachea is when we cough. And the question is, for what value of small r is the velocity maximum? So let's see how we can solve this exercise. We have an equation for the velocity, so when we look for the maximum, we want to find the candidates and then find which one satisfies the first derivative test for a maximum. So v equals k times capital R minus small r times r squared. When we take the derivative of y and we write y prime, it usually means dy dx with an x at the bottom. If you use another variable, like if you take the derivative of y with respect to t, oftentimes we don't write y prime. We avoid that. Y prime, we tend to save this prime sign for x's. But if it's absolutely unambiguous what you're differentiating with, you can use y prime all the time. Here, if we write v prime, it's completely unambiguous, so there's no problem, but we may want to talk about the derivative dv dr just to be more specific, the derivative of v with respect to r. Before taking the derivative, though, I'm going to distribute this. K capital R minus kr times r squared, remember the parenthesis, equals kr times r squared minus kr cubed. Now I've finished distributing, and the reason is if I want to take the derivative, it's going to be much easier with a polynomial than here where I would use the product rule. If you use the product rule, great, but distributing first made it easier. So the derivative of that is this k times r is a constant, so when we take the derivative, we have 2kr times r. And likewise, k is a constant, so the derivative of this term is 3kr squared. So now I can factorize some of this again. I can factorize k, and I can factorize r. So it becomes kr times 2 capital R minus 3r. So we want to find our candidates for what values of r is dv dr equal to 0, for what values of r is dv dr undefined, and if there are any, what are the endpoints. So group number 1, dv dr equals 0. When is this equal to 0? When r, either this is 0, so r equals 0, or this is 0 here, which means r equals, so I need r, small r to be 2 capital R over 3. When is dv dr undefined? I had a polynomial, I was working with a polynomial, so the derivative is never undefined, never. And finally, are there any endpoints? If we look back here, r is greater or equal to 0, so there's an endpoint on the left, and there's no endpoint on the right because there's no equal sign. So this r equals 0, we happen to have it here already, so that's that doesn't add really any candidates. Let's make a number line. We have an endpoint on the left. We have an open interval on the right. And r equals 0, r equals 2/3 capital R. And now I'm interested in finding the sign of dVdr. So since we're not working with numbers strictly, but we have this constant capital R, it makes it a little bit harder. What is a number between 0 and 2/3 R? For example, 1/2 R. You can pick 0.1 R, or any number that's less than 2/3 times R is going to fit. So let me see what happens when I plug it here. This is positive, and now I have 2 capital R minus 3/2 capital R, because R is equal to 1/2 capital R. So 2 capital R minus 1.5 capital R, this is positive. So I have positive times positive, that's positive. Think about it, and you'll figure out how it works. Now for this side here, I need a value that is greater than 2/3 capital R. Maybe I can take 3/4 capital R, or I could take 0.9 capital R, and I'm gonna find the sign of this. So k times R is positive, and if I plug in R equals 3/4 capital R here, I get 2 capital R minus 9/4 capital R, that's negative, so I get a negative sign here. And therefore, according to the first derivative test, V is maximum when small r equals 2/3 of capital R. That's it for our first question. Let's move on. We are now going to have a look at a little part of exercise 109, the easy part. This is the reason why we're not doing all of exercise 9 is just because it's very long in terms of computation, but we will discuss question B and C. So, in this exercise, we are looking for a polynomial that has the specific extrema that are given. So in exercise 109, we're looking for a polynomial that has a minimum at 0, 0 and a maximum at 2, 2. Question A only asks us to determine the smallest possible degree of the function. So what is the smallest polynomial that can have a minimum at 0, 0 and a maximum at 2, 2? Let's sketch it. So we need a minimum here, and we need a maximum here. So it looks like the smallest function is going to look something like that. And this answers our question A. It looks like degree 3 is the minimum degree. If we have degree 2, it's a parabola, so it wouldn't fit. Now, we are not going to do question B, but the question is, what is that polynomial? What is that cubic function that has the property of a minimum at 0, 0 and a maximum at 2, 2? To do that, you would need to write the general equation of a cubic function, ax cubed plus bx squared plus cx plus d, and we have 1, 2, 3, 4 unknowns. So we will need 4 equations in order to solve this problem. And the 4 unknowns, or the 4 equations are 1 for the point, 1 for this point, 1 for this slope, and 1 for that slope. So let's start. We won't solve it, but if we want this function to go through 0, 0. It's 0 equals a times 0 plus b times 0 plus c times 0 plus d. So d equals 0. What about the point 2, 2? It means 2 equals a times 8 plus b times 4 plus c times 2 plus d. But d equals 0, so we can just ignore this. That's one equation. And now we can work with the derivatives, because we know the derivatives are 0 here and 0 here. So the derivative of y is 3ax squared plus 2bx plus c. And we need this to be 0 at x equals 0, since we have a horizontal tangent line. That is going to be 3 times a times 0 plus 2 times b times 0 plus c. So just c. This yields c equals 0, which we could put back here to get rid of the plus 2c now. And at x equals 2, the derivative is also 0, so it becomes 3 times a times 4, 12a plus 2 times b times 2, 4b plus c, but c is 0. That's another equation. So this is how you would solve this exercise if you went on. You would now find a, find b. Oh, there should have been a b here. Find a, find b, and then you can write the cubic function with a, b, c, d. But that's just a lot of computation. Finally, we're doing two exercises about true and false. Is it true, is it false? We need to explain or exhibit an example that shows that it's false. The sum of two increasing functions is increasing. So we have two functions, let's call them f and g, that are increasing, f and g, and we want to show that if we add them, we'll get an increasing function. So we could try and do that graphically by just adding these two functions, f plus g. I need to add this little piece here on function g. Here I need to add this to function g. Here I need to add this whole thing to function g, so maybe I'll end up here. At this point it's easy because g equals 0, so my function f plus g is going to go there. Here I need to add this and that, so I'll end up maybe up here. So in the end, I could roughly get a function f plus g. It appears that it's increasing always, but it's not a very convincing argument. Better is to think about derivatives. If f is an increasing function, what it means is that f prime of x is greater than 0 for all x. And g prime of x is also increasing, so g prime of x is greater than 0 for all x. So now I can think about the function f plus g. F plus g, if I want to figure out, let's write, is f plus g increasing? To answer this question, I need to study f prime plus g prime. What I want is to find the derivative of f plus g. And we know that this is just f prime x plus g prime x. So since this number here is always going to be positive and that number is always going to be positive, the whole thing is also always going to be positive. Therefore, f plus g is increasing because f plus g prime is positive everywhere. Now in the next question 114, we wonder whether the product of two increasing functions is increasing. So we can maybe start again by making a sketch. Let's say one is here, this is f, and this is g. So how do we multiply f and g graphically? Here, this is a number less than 1, so if I multiply a number less than 1 by this, let's say it just goes perfectly through -1, it's going to end up right there. Here, it's exactly 1, so if I multiply 1 by g, I'm going to get exactly g. It's already much less clear whether this is always going to be increasing. Of course, this is only a sketch, so we can't conclude anything from here, but it's really not very clear. What about that point here? It's even smaller than there, so when I multiply with that, it should give me something that's smaller, but since this is also larger, we don't really know where we are. It's not very clear. Definitely later on, when we multiply this number with that number, it starts to become bigger, but we don't know. However, we can think in terms of derivative. F times g prime is f prime times g plus f times g prime. So is this always positive? That's not clear at all. We know this is always positive. We know this is always positive. But what about g and f? The g can be negative. Actually, it's negative here. F could also be negative, even though in my example it wasn't. And if g and f were both negative, that would be negative, that would be negative, and we would not end up with a positive number. So here we are kind of convinced that the answer to 114 is no. F times g is not always increasing. I'll find now an example that shows why this is definitely not true. And the easiest example we can find, we need to find a function where g is negative and f is negative, even though they are positive, that their slope is positive. And I think if we choose f of x just equals x, and we choose g of x equal x as well, what is the product of f and g? F times g of x is x squared, and we know what x squared looked like, and clearly it is not increasing everywhere. So not increasing. Counterexample, if f of x equals x and g of x equals x, then f times g of x equals x squared, which is decreasing for x less than 0. So that's a counterexample. It shows that the answer to 114 is false.